So we are facing the last three lectures. Let me tell you first of all what I'm going to do in these three lectures. There are basically three topics we need to tackle, which finally have to do with AI. Last lecture we discussed how it is possible to obtain in a data-driven approach the ideal collective variable, how this can be used to obtain important kinetic information, for instance, to cluster the presence of configurations in a dynamic and aware way, thereby being able to identify configurations that live in the same states. This can, for example, provide the basis for building a microstate model. Okay? I call it machine learning because I'm not using any physical information, analytic information model. I'm just taking some data and building some data-driven approach that yields me some physics information. Without asking the nature of the data, but basically manipulating the data as such. Today we're going to dig a little bit more into this learning the intrinsic manifold and understand how it is possible to use these concepts to devise schemes that explore configuration space very actively. Maybe it can be used to facilitate the building of microstate models. Next, we're gonna have a short lecture, probably today or next lecture, on the concept of reaction coordinate, which is closely related to collective variable, but does not necessarily correspond to it, and we identify the ideal reaction. And finally, in the last 1/2 lectures, we're going to see how AI and machine learning can be used today in a few applications of molecular simulations, from force field to exploration in conjunctions with the concepts that we have just described, the collective variables and the reaction. Okay? So, first of all, I think from the logical perspective, what I will do today is to introduce the concept of ideal reaction coordinate, and then do machine learning applications with collective variable and reaction coordinates. Okay? Okay, the concept of reaction coordinate falls within the category of the statistical physics of reactive processes. Reactive processes is simply some events that occur at equilibrium or out of equilibrium. We will be mostly interested in whatever occurs at equilibrium. Check if this is actually going. Yes. Where you start from a certain region of configuration space, which we call R for reactant, and end up in a region of configuration space that we call P, product. Now, if you look at the molecular dynamics trajectory, typically a molecular dynamic trajectory does not contain only reactive processes. Now, in this lecture, I will be working under the simplifying assumptions that there are only two metastable states. There could be more, or there could be a hierarchical structure such that within, say, the R state, there are subspaces that interconvert on a faster time scale. All of these complicancies can be dealt in a Russian doll kind of scheme. For instance, if you understand how to deal with reactive processes between two states, and you're all of a sudden at third state, then you can apply this concept individually for studying each of these transitions, right? And the same happens is within the reactant state, there is R1 and R2. You can study the same idea to study the transition between R1 and R2. Okay? So, the simplifying assumption in which you consider only the two states is not just reducing the number of applications, is the building block for more complicated and more complex reactions. Okay? So now let's look how a typical molecular dynamic trajectory would look like in a space with two states. Well, if you start from these states, the system will spend an exponentially long time exploring, or occasionally venturing out of the state and re-entering it because of thermal fluctuations. Sometimes we go to a state that is somewhere in between, and so making very large fluctuations, almost making it to the other state, but somehow returning before making the transitions. And quite rarely, these fluctuations are taken to this place, which now very intuitively, at the moment, I refer to as the transition state. Then the trajectory will make it to the other product and begin a normal oscillation to the product until you get a trajectory that goes back. Now, at the moment, we refer to as the transition state as the state from which you're typically rolling into the product. But we will give a much better definition in a moment. You might think about it in a two-state with an energy barrier. The transition state is clearly the top of the barrier, because after you pass the top of the barrier, the system is drifted to go to the other state. But conformational transitions are often driven by free energy barriers rather than energy barriers. And the transition state might not be associated with an energy barrier. For instance, in the usual example we've been using several times in this course, in which there are two holes at the side of the room, the transition state may be the hole there within the door that is left open. Now, there is no energy barrier as the particle goes through the door. It's not going uphill, but it's an entropic barrier because the number of states that allow you to go through the door are small. Okay? So the transition state is sort of, at this level, sort of an elusive concept, but it will become more precise in a moment. Now, what I want to focus on is that in many cases, we are interested in transitions, in understanding transitions. For instance, we might be interested in understanding how an allosteric regulation works, or how a protein folds, or how a protein misfolds, or RNA changes conformations. So we might be interested in what happens while the system really performs the transitions, and we might typically be less interested in whatever is not associated with the transition, but just as a thermal oscillations. So in the conventional statistical mechanics we learn during the bachelor degree, we deal with all of these statistics at once through the concept of equilibrium distribution. And equilibrium distribution will only give me one stochastic descriptor, the probability at equilibrium to find the particle at a given point of configuration space. I'm leaving out momenta, I should say phase space, but in all these simplifying assumptions I'm having in the back of my mind to think about, say, overdamped Langevin dynamics where there's no momentum. And typically, when I study conformational transitions, I'm less interested in momenta than I am in configurations, because momenta change very rapidly because of thermal fluctuations on the picosecond. Okay? So in equilibrium, where all of my statistics is dealt together, so in Gibbs statistical physics, I don't make any distinction between transition sections of the path and equilibrium part of the path. They're all together under the long ergodic trajectory by which I compute time series, which I then identify with phase space series. Remember this part of the course. Now we want to do something different. We want to build a statistical physics that is only pertinent to the reaction pathways. So first of all, I could give you a mathematical definition of reaction pathway, and you'll find it in the notes. but I will be on a higher level in this part of the course because I want to give you the ideas. And I will ask only for higher level information in the course. Intuitively, a reaction pathway is the subpart of a longer Goddard trajectory that only contains reactive part. So a transition pathway rather than reaction pathway. So transition pathway. I have my reactant, I have my product, I have a part of the trajectory in which I perform thermal oscillations, part of the trajectory in which I explore and I come back. And then I have a number of trajectories in which I explore and I reach the product in either directions. Okay? And I have many of them. So, if I'm interested in understanding from a statistical physics perspective the reactive process, I basically have to get rid of everything that is not a reactive process. And basically rebuild in statistical physics using only this part of the ergodic trajectory. So again, intuitively, I call a reactive process any trajectory such that if I go back enough, the last time I defined two surfaces, basically the border of the reactant and the border of the product. And I call a reactive trajectory a trajectory such that in any point of the trajectory, the last border I visited was a reactant border, and the next one would be a product border, or vice versa. But I will not call a reactant pathways anything that would be the last border I visited was the reactant and the future border that I will visit is still the reactant, or the last border I visited was the product and the future would be the border that I crossed was again the product. Okay? This is a very intuitive definition. I could write this in terms of x of t, there exists a t such that the x of t plus belongs to a surface. This is just a mathematical encoding of whatever I said. So transition path theory is the statistical mechanics of in which follows from analyzing only transition paths. And I find it quite amusing. The transition path theory is a relatively new invention. I would say 2000, I might be wrong by a few years, a couple of years, but I would say 2000, 2005. Could be 2005, 2007, something like that. And of course there have been several people contributed to develop it, but I think there are, the community would agree there are two main contributors. Eric van den Eyden on the one hand, and perhaps Gerhard Harmer and collaborators on the other hand. People who are still around and my age or probably a couple of years older. Yes, Eric van den NYU, and Gerhard Hammer I mean, I should say Gerhard Hummel with 2 M's. I should say there will be many others who give important contribution, and I should apologize to them for not listening, but I think these 2 people are those who led this discussion. You'll find lecture notes of these people with collaborators in the internet if you want to find out. So I will not develop the entire transition theory, which was part of this course in its more theoretically oriented formulation. If you look in my YouTube channel, there is a more detailed description of all of these concepts, following from a previous course I gave, statistical theory. But I will just mention the main result. Transition path theory encodes more information than equilibrium gives statistical mechanics, which seems strange because it is based on lower samples, like you make a filter. But sometimes in removing lies information, right? So in the fact that we focus on transition pathways, it means that we're being more specific. And to describe something that is more specific requires more stochastic descriptors. And I want to give you a hint of what these stochastic descriptors are and why are they important, and what is the relationship between these stochastic descriptors and equilibrium thermodynamics. But already you know that in a reactive process, 2 fundamental informations, pieces of information lie. Number 1, the mechanism of a reaction. How does it occur? The flux of probability, if you want, right? And second, the rate at which it occurs. So you see already you have objects that are not there at equilibrium. At equilibrium, you don't talk about rate. Rate is something that has a dimension of 1 over time, and there's simply no room for time in equilibrium statistical physics. I mean, in the theory of the ensembles, okay? So in transition path theory, or in short T, P, T, there are 3 major stochastic descriptors. The first one is the commuter function. Which, as we shall see, represent the concept of ideal reaction coordinate. And I will have to tell you what all of this means in a moment. So what is the commuter function? The commuter function is a quantity that tells you how far you are in a reaction. And it does that in terms of a probability. The commuter function is a probability that if you start from a given configuration, or a point in phase space, but we will stick to configuration space, like I said, and neglect the phase space contribution. Say I'm starting from X. The commuter function is the probability that if you start a molecular dynamic simulation from X, or physically, if your trajectory starting from X, will cross delta P, the border of the product, before crossing the reactant. So it's the probability from 0, 1 of reaching P before returning to R. How much you are committed to make it. Now, I should say this is more technically speaking the forward commuter. You could define the backward commuter as the probability of going back to R before you make it to P. So clearly, configurations that are very close to the border of R will have very small values of forward committers. configurations that are very far in R, in Q, very close to P, will have very large values of forward committers. Right? So, regardless of a statistical weight of the configuration, I can assign a value 0 or 1, from 0 to 1 to any point in configuration space. Because the committer is not a probability density like the Boltzmann distribution. If I am in a very unlikely region of configuration space, say a structure bond, the Boltzmann weight will be very little. Yet, from that configuration, the committer function will be a value bounded from 0 to 1 because it's a probability, not a probability density. Okay? So this means that the entire configuration space can be foliated in hypersurfaces of dimension 3n minus 1 that are characterized by a given value of the committer function. And the transition state is now properly defined as the isocommitter surface with Q1 half as the ensemble of configurations from which you have 50% probability to make it to the product. Right?
So the isosurfaces they are continuous?
Typically, yes. Because now, if I were to dig into the statistical mechanics, people have discovered what equation defines the commuter function. And it's a differential equation. The adjoint of the Fokker-Planck operator on Q going to 0. This is the equations. So the Boltzmann distribution obeys H F Fokker-Planck Boltzmann distribution equal to 0. And the commuter function obeys H dagger equal to 0. Also, Q has different boundary conditions. Is bounded to be 0 here and bounded to be 1 here. Right? So Q at dr equals 0, Q at dp equal 1. I now want to dig into the fact that commuter is the ideal reaction coordinate. Now, the concept of reaction coordinate has been a cornerstone of physical chemistry for decades. It's the notion through which physical chemists understood the concept of progress of a reaction before this transition path theory became formalization of that into statistical physics. So, the chemist has this idea that a reaction proceeds mostly forward in some implicit coordinate. What do I mean? Remember, at some point, we invented a particular type of stupid paradigmatic model that was designed to make things complicated. The reactant and the product had different x and y coordinates, but neither x nor y was a good reaction coordinate. And this will become even more evident if I make this non-monotonic in y. Right? Neither x or y really allow you to tell you if you're going forward in the direction, in the process, because here I'm moving forward in x, and I'm moving forward with the reaction, so you're getting closer intuitively to the product. But here I'm moving forward in the reaction, but I'm going backwards in x. So clearly, I cannot simply measure x to know how far am I gone in the reaction. Right? Similarly, y, if I've made this detour here has a similar property. I'm going down and then coming back up before I go down. Now, clearly though, you can think about, if I look at the typical processes, if I make an average over all the processes, and I look at the trajectories of all these processes that make it, well, I could invent a curvilinear zigzag that follows the mean path here. And if I were measuring the mileage over this curvilinear zigzag, right, I could sort of tell whether I am going forward or backward in the reaction, right? So this notion of reaction coordinate was rooted into physical chemistry, but it is very simple to invent situations where it becomes a little bit tricky to interpret. For instance, think about a reaction which has multiple channels. For instance, you have a reaction, a product, now you have a mountain, and you can go left or right to the mountain. Now, the mean path probably crosses exactly the mountain, which is where particles never go. So, the concept of reaction coordinate was for a long time subject of discussion. What is a reaction coordinate? Can we define it in a proper way? People didn't know how to do it, but people knew at least property that the reaction coordinate should satisfy. It should distinguish between reaction and product, for sure, because it has to be minimum in one value and maximum in the other, or the other way around, the sign would be the other. And again, in total analogy with the collective variable, it should be the slowest collective variable in some sense, because the progress of the reaction should be such that, in other words, all the orthogonal direction to the reaction coordinate, right, should be crossed at the configurations, let me say it better. The orthogonal direction here should be basically thermalized, right? Remember this idea of adiabaticity. But what does it mean? It means the reaction pathways should cross a given value of the reaction coordinates in a point, and the distribution of crossing the value of the reaction coordinates restricted to the fact to be that particular value, the reaction coordinate, should be Boltzmann. That's what I mean orthogonal thermalization. In other words, if I build a histogram here of where do I cross the reaction coordinate, okay? This histogram should be proportional to e to the beta u. Okay? This is how we say that the orthogonal direction is thermalized, because it is the distributions at fixed value of collective variables is distributed according to Boltzmann. So these were the two properties that people sort of had in mind. It should intuitively give you a sense of forwardness in the reaction. It should distinguish, and it should be very small to the point that I could think about everything else to be thermalized. Now, it turns out that the commuter function precisely fulfills this property. And I'm going to show you why. Let me ask you two very similar questions, which nevertheless are not the same question. Okay? The First question is, at equilibrium, what is the probability to be at configuration X? Let's divide configuration space into reactant, product, okay, and transition state. And transition state is configuration space minus this and this, so everywhere else, right? Transition region. Let's be X a point of the transition region. Let's call it omega t, okay? One question is, what is the probability to find at equilibrium the configuration at X? And the answer is very trivially probability to be at X at equilibrium to find the system in the point X is given by what? The Boltzmann distribution. So this is what we already knew. And this is what happens if I retain the entire ergodic trajectory. Remember? Because the equilibrium distribution comes from making statistical physics of long-time series with the entire ergodic trajectory and then imposing the ergodic assumption that you can replace that with the phase space averages. Remember that? But now we want to make a second question. What is the probability to be at X condition to be at the transition path? So in other words, the probability that X, I have now two independent requests, that I find a particle at X, and I find the particle at X while X was living on a transition path. For instance, I want to exclude in counting the times that I visit X, the times that I visit X by fluctuations that returns in the reactant. So when I define the equilibrium probability, anytime a trajectory crosses X, I add a beam in the frequentistic histogram that defines P of X. Right? In the second probability, I add a beam only if X is visited by a transition pathway. Okay? This quantity is called the transition path density, sometimes called M of X. Transition path density. Transition path density. Okay? Now, let me ask you, what is the transition path density near the reactant? Eh? No. What is the probability that I visit the point X near zero? Because most of the time that I visit X will be by thermal fluctuations. Right? What is the transition path density near here?
Near zero.
Again, zero. The transition path density will be largest in the middle, where the probability of reaching that point will be small by thermal fluctuations from either sides. Okay? And in fact, it's almost immediate to derive an equation that relates the transition path density to the conventional density. The transition path density is equal to, now I could give you a formal proof of this, but again I'm giving you the intuitive proof, okay? Heuristic intuitive. Is the probability of finding visiting X at equilibrium conditioned to be on a transition path, right? So the probability of being on a transition path and the probability of visiting X at equilibrium are two independent requests. So the probability is the product of these conditions. Right? So clearly this will contain a Boltzmann factor, which is the first condition, the probability of visiting X. And now I have to add, well, there will be a normalization here. Let me call it ZT, which is not a Boltzmann distribution. This is not just a partition function, because this is normalized only to the transition region, and because there's another thing that we need to account for. But this is a normalization that will make this one integrated over the entire transition region. Okay? Now, here we want to add the request to be on a transition path. And it's quite simple. The probability to be a transition path means that if I am on a transition path, with the probability given that I have a probability Q that the rest of this transition will go to R, and then a probability to go to P. Sorry, to R to P. So I will have to multiply two probabilities that I've reached X from R, and I will reach P from X. Right? So this is in fact the product of two probabilities. The forward commuter is the probability that I will reach the product from X, right? And then we call it Q rather than Q forward. And the backward commuter, or Q minus, which I will write in a minute, is the probability well, what I want here is the probability that I've reached X coming from R. But now if you think about it, this is the same as asking if dynamics is Markovian. It's the same as asking, well, the probability that I will reach the reactant from X. So what happens here is that this is actually 1 minus Q of X. Q of X. So this is the probability that X belongs to a transition path. This is under Markovianity, blah, blah, blah. If I want to do a formal derivation, I would have to invoke Markovianity and macroscopic reversibility. These are all concepts that we did not dig very deep into. Yes?
This accounts for both ways, or is it just count from R and blah?
Yeah, this is accounting for directional definition of the action paths. If I want to do the opposite, I have to switch Q with 1 minus Q. But you see, if I switch Q with 1 minus Q, what I'm simply doing, I'm reversing this. So the transition path density doesn't change. So this first of all tells me what the stochastic descriptor is. But it also tells me that the Q is the ideal reaction coordinate, because I now may ask, what is the probability by which transition pathways intersect a given Q bar isocommuter surface, and hypersurface of fixed value of commuter, say 0.1, half, or 75%, or right, let's say Q bar be a given probability. Well, it's the transition path density at the given value of Q, right? So, on an isocommuter surface, on an isocommuter surface, so on the surface made by points with identical value of commuter, okay? M of x is Q bar, 1 minus Q bar, times Boltzmann, right? On the isocommuter. So you see, it obeys exactly the property that I've asked. The pathways intercept an isocommuter surface with a distribution that is precisely Boltzmann. Okay? So we see that, in fact, the commuter function is the ideal reaction coordinate. Because it distinguishes between reactant and product, and is the slowest variable in the sense that the orthogonal distribution is Boltzmann for transition pathways. Okay? So the long-standing problem of how do we define the reaction coordinate, I think most colleagues would agree has been sorted and solved by the concept of commuter function. Of course, it doesn't mean that we can do it. It can only mean that we can define it. However, and here we begin, it is relatively simple, at least from the conceptual point of view. Okay, sorry. Let me rebuild this sentence to make it slightly more logical. We have a definition of the commuter function. There is a definition based on mathematics, and pretty heavy mathematics, because we have to solve a partial differential equation that is as complicated as the Fokker-Planck equation to get a commuter. It's the adjoint of the Fokker-Planck, the stationary Fokker-Planck equation. It's basically a 3n-dimensional partial differential equation with no trivial boundary conditions. So, not a simple object to do, right? So, even though the commuter function formally represents the solution to the problem, how do I define a collective variable that completely describes the evolution of the system in a reaction, I am left with a problem of finding an efficient way to compute it. Okay? And so I want to draw a parallelism with what we did in the previous question, in the previous lecture. In the previous lecture, we were concerned with the concept of intrinsic manifold dimension, and what are the ideal collective variables. And we came to the conclusion that the collective variables had to do with the lowest left eigenvalues of the Fokker-Planck equation, or the lowest eigenvalues of the adjoint Fokker-Planck operator. Remember the Ln. Why? Because the kinetic distance was an Euclidean distance in the embedded space of these left eigenvalues. Remember that? But then we had a problem, how do we compute those left eigenvalues given a set of data points? And we came to this idea, we concluded that diffusion maps are a data-driven algorithm and process that will embed configurations in the space of ideal reaction coordinate. Remember that? Now we are facing a similar problem. We asked what is the ideal collective reaction coordinate, which is an even simplified version, because you see, collective variables are multidimensional objects, but they apply to both equilibrium and non-equilibrium, right? You can just project onto the collective variable space both an equilibrium or a transition path, right? The reaction coordinate only applies to transition processes, correct? But it's a one-dimensional object. You don't need n collective reaction coordinates. You have one collective reaction coordinate. We came to the conclusion that the commuter function is the ideal reaction coordinate. But now we are left with the problem, how do we compute it? Okay? Now, I will not go into the detail, but let me just tell you that this is really contemporary research. I think there are contributors to these questions that publish very relevant results, if not this year, last year. So you really are talking about, now we're talking about frontier research. and I probably want to mention a couple of names here. Peter Bullhaus. This, by the way, is the inventor of transition, one of the inventors of transition path sampling, the algorithm to sample transition path that we discussed earlier on in the course. Roberto Comino, also one of the main authors. And so basically, what do the people do? They mix transition path sampling with neural network. I am now about to tell you in a very qualitative way how the committer function can be estimated. Okay? So remember transition path sampling. Transition path sampling was a Monte Carlo approach in the transition path space. So it worked like any Monte Carlo. You start with the initial element of your Markov chain, which has to be a path, because this Monte Carlo produces paths. So you have to have a seed path. You would pick up a point in the seed path and shoot two configurations. And if you have a dynamics which contains velocity, like under Lagrangian dynamics, they have to have consistent velocity. This velocity has to be negative of the velocity of the other side, with the two trajectories. If you have only Lagrangian dynamics, it will have overdraft Lagrangian dynamics, it will have velocity, but you shoot two trajectories. And if both end up in the product, you discard because it's not a transition pathway. But if both end up in the reactant, you discard for a very simple reason. But if one of the two gets to the reactant and the other one gets to the product, you have made a good move for the next transition path. And then you have to accept it or reject it according to some probability. Because that's how Metropolis Monte Carlo work, right? Now it turns out that in most cases you accept it or reject it. Only the condition to have a transition path is sufficient to grant acceptance. But this is technical, we don't need to care about it. Okay, so you have a certain probability of acceptance. So by doing this, you generate transitions and samples. It's a costly object. Clearly, you want to choose the point from which you shoot very carefully. Because from what we have discussed now, it is clear that if I choose this point to shoot, I will have a large probability that one branch of the trajectory will fall back into the reactant. You see? And this probability will be Q minus, or the backward committer. But I will have a very small probability that a trajectory will get into the product from here. Because the probability to be on a transition pathway close to X is very, very, very small, right? Vice versa, if I shoot from here, the probability to get a transition, likewise, sorry, not vice versa. If I shoot from here, the probability of two trajectories to generate a transition pathway will be very, very small for the same reason, right? So most of my choices for which to shoot should be more or less in the middle. Okay? Where the transition pathway probability would be low. So, clearly, these examples, it just illustrates, I believe, in a very clear way, why the notion of committer is very important to inform efficient transition path sampling. Right? The distribution from which I will shoot should be picked around the transition state. But if you evaluate Q, 1 minus Q at the transition state, you get 0.5, 1 minus 0.5. That's 25%. Right? That's the maximum. So 3/4 of the trajectory, even if I shoot from the transition state, 3/4
of the trajectories that I will generate will be scarred, at least. So 75% is 25% is the maximum theoretical efficiency of transition per sampling. Right? So this already tells you that transition per sampling is a fantastic algorithm, but you cannot hope to have more than 75% of, sorry, 25% of acceptance probability, which is actually an upper bound. So it's very important that you don't go very much below that upper bound. Right? So knowing the committer and have a fairly good idea from where to shoot is of dramatic importance to have decent transition per sampling algorithms, right? Of course, it's very simple in the one-dimensional example where you hit the top of the barrier. But remember, you have a molecular configuration in a 3n-dimensional space. You have no idea what isocommitter surface does it belong to. So, what do people do? They build self-consistent schemes in which they have this exploration-exploitation dilemma in which they, as they start doing transition per sampling, right, they collect information on what is the committer values in a given configuration. Why? Because they don't shoot one trajectory, they shoot 100 trajectories for that configuration. And they count how many times you get the transition path, how many times you get to the reactor, how many times you get to the product. Right? So by shooting many trajectories, you begin gaining information about the value of the committer in the path. Okay? But rather than just storing this information there, you use this information to train a neural network representation of the committer that takes in input some features, so as you shoot to get transition per sampling, okay, you also train a neural network where you have some features in input we take from X, for instance, the dihedral angles. Okay? You have a, I'm going to write this in a very schematic way. This is my feed-forward neural network. And in output, I have a value between 0 and 1 that I call the committer. Actually, technically, they map the continuum, the committer into a function that goes from minus infinity to plus infinity. It doesn't really matter for us. So, what do? You start doing transition per sampling algorithm. You start learning what is the committer configuration by configuration. And you use this as training data to build a neural network representation Q, neural network representation of X by supervised training. You follow me? And as your information about this gets better and better, you use it to get more and more efficient choices for transition per sampling. Yes?
What if you need only to find, you have to find the point where basically Q is 0.5, then why do you need to reconstruct all of Q?
That's a very, very, very good question. In principle, you need a committer in the vicinity of the transition state. Of course, you want a function, so you get a configuration X in input, and is it good or is it bad? No, I mean a binary representation that says this sits exactly in the transition state, meaning 1, it doesn't sit in the transition state, meaning 0, is a bit too risky because the probability that you find an X that sits exactly in the transition state is 0. It will be always in the region. So for computational purposes, what you need is a range of values of Q around the transition state. And therefore, you build a network representation. Since most of your sampling will be driven to configuration of isocommitter, your representation will be bad here and bad here. And will be most accurate here.
What I meant was, if you just you start in a random point, and then you sort of gradient descent towards, you build a function which has 4.5 as the minimum.
Yes,
and
yes, but you
then-
need a function. I agree, but you need that function. You cannot just get I am at the so you always need a representation of Q. Whether then you want to do gradient descent to get values that are as close as possible as Q.5, I agree. And by the way, you cannot really do gradient descent because this representation doesn't know about molecular constraints. So if you do gradient descent, it's very likely that you get a configuration that is not a molecular configuration. So basically, you want to be you want to have an idea whether it's a good starting point or not, and then maybe you want to sample your initial configuration from Q1 minus Q, where Q1 minus Q is learned from your data. So if you're only interested in improving sampling, all you need is a good stochastic representation of Q of n in the transition region. There are other applications for which you also want very accurately this, which are very difficult to compute. I will not be interested in that. That you need something else called transition interface sampling, and this goes way beyond. But what I'm trying to say is that neural networks and can be trained on molecular simulations to give you a mathematical proxy for the commuter, and as long as you get a better proxy of the commuter, your efficiency in the very same algorithm that leads that estimate will improve. So maybe you start with a 2% accuracy, and you end up with a 20% accuracy. So you see how machine learning in this case can take you a long way, because once you have generated a good estimate of Q, then you can do a good transition path sampling, and therefore understand better. And then if you make an histogram of this point, they will reflect the transition path density. Okay? So again, collective variables apply to both equilibrium processes and transition paths at equilibrium. Reaction coordinate is a process, is a concept that is deeply rooted into transition paths only. Left eigenvalues of the Fokker-Planck operators below the gap are the ideal reaction coordinates, but you have the problem of computing them, and diffusion maps is a numerical way to estimate them given a collection point at equilibrium. The commuter function is the ideal reaction coordinate, and at least this algorithm is a plausible way to correctly estimate it in terms even of a neural network representation, exploiting the fact that neural networks are universal approximators. Now, just finish my sentence. What we do, for instance, and other people I'm sure have done, is to build other type of approximations of Q that are variational approximations. So there is a variational principle associated with Q. I will not go into that. Okay? And you can use that variational principle to make a variational ansatz and try to get a better choice. So there are many approximations, but this is the most machine learning driven approximation. Yes?
Do you get how to fix the features?
Sorry.
How
The features.
the features of the
Okay, so yes. So neural network requires inputs, right? In principle, you can choose your own inputs. In principle, my features could be all the Cartesian coordinates of all the atoms, which means that my feed-forward neural network would contain a lot of inputs, and but most of the configurations, most of the values that I can feed in do not correspond to molecular configurations, because I have gazillion ways of organizing Cartesian coordinates that do not correspond to molecular configuration, because you break all sorts of bonds. So, if I use that as input, my network will have to learn it somehow implicitly. It That means that we need a lot of parameters to train. So featurization sometimes is useful because I, for example, use the set of dihedral angles. Now, dihedral angles already parameterize molecular configurations only, right? So likely dihedral angles reduce dimensionality, and on top of that, require the network to learn less information from data. Okay? So anytime you can provide the network a pre-digested input, where some constraints you want the result to satisfy is already built in from the scratch, such as local translational invariance and blah, 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 you always want to do it. That's why you typically first pre-digest the molecular Cartesian coordinate into features, and you give these features to the network. Okay? Okay, so do you follow me so far? So this has been very important because I like this because it's a very nice example of how machine learning is integrated with molecular simulations today. Learning the commuter from simulations and using the commuter to get better simulations. Another way in which machine learning gets used is, for instance, through automatic differentiation. If you need a function to be differentiated many times, machine learning algorithm for automatic differentiation that we build for training networks basically are very, very efficient ways to do that. So you want the gradient of the potential. Okay? A third way, which is essentially the same way, but say you now, let me give you one more application. Say I have now equilibrium distributions that I sample from Monte Carlo, molecular dynamics. Not for transition pathways, say, but for any equilibrium process. So taking the entire phase space average, okay? And suppose I've used collective variables to project these onto the dimensional data. Okay? Likely, I could have used, for instance, if I do this in an exact way, in a rigorous way, I could use diffusion maps and project onto the ideal reaction coordinates, collective variables. But I could also have used some physics intuitive driven collective variables and do exactly the same. Say I have my equilibrium data projected onto CV1, CV2. This could be diffusion maps or heuristic diffusion collective. Very likely there will be regions with high statistics, small regions with low statistics, and then I have some like leopard skin structure with spots, dark and light spots. A large effort in the community has been done towards developing smart interpolators to fill in the gaps. Okay, naive way would be I feed forward these into supervised learning. Clearly, if I do it the naive way, all the information where the real data is there can be completely hallucinated in the network because the network doesn't have enough training data. So people have done all sorts of combination of Gaussian processes or supervised training and more and more sophisticated ways of doing this that use physics information built in different through controller or all sorts of advanced architecture. Clearly, these schemes upon which there is a lot of research allow me to get the best Bayesian inference about regions that are poorly explored, trying to resort on the continuity of the function, meaning the function is smooth, so I know the information here, I know the information here, I have reason to extrapolate. So much of the research in this field goes on, and it's a little bit like what you do with the committer, but only in a multidimensional space of collective variables. Okay? So that's another key application of machine learning today to molecular simulations. Okay? So once again, wrapping up, we introduced the concept of reaction coordinate, we introduced the concept of transition path density, and we saw that transition path density are linked to commuter and to Boltzmann distribution, and this linkage is what allows me to identify the commuter function as the ideal reaction coordinate, because on isocommuter surface, the transition path density is distributed according to Boltzmann. Okay? I want to close this lecture to tell you that transition path theory requires one additional stochastic description. So, transition path theory is the statistical mechanics of transition paths. Unlike conventional Gibbs statistical mechanics, it does not only have the Boltzmann distribution, actually it does not have the Boltzmann distribution. It has the transition path density that replaces the Boltzmann distribution. Because of the probability of finding a particle X conditioned to be on the transition path. And this is even in terms of the commuter function and the Boltzmann distribution. I'm repeating things I've just finished saying. And the commuter function itself is a second stochastic descriptor. But I want to now emphasize that these two alone are not sufficient to give me the entire information I need to characterize a transition. I need one more. And I want to unveil what this one more, the stochastic descriptor is. Okay? And to unveil what this extra stochastic descriptor is, I rather do an example that illustrates that, hopefully in a as clear as possible way. Suppose I have a reactant state. Suppose I have a product state. Suppose I have an intermediate state along the way, maybe a metastable state. Okay, for instance, a protein is trying to fold, and it first forms an hydrophobic core with a terminal helix still floating around, and the system spends a long time swinging around this terminal helix before the helix eventually docks onto the system, thereby making it to the final state. Okay? So we have a transition state. But sometimes, and actually more frequently than one would think, from the transition state, I could go to what I will call a transition trap, a trap. What is a trap? Is a configuration that does not sit on productive transition pathways. So for instance, in the example that I was just making it, this is my protein. Please look at me. It has mostly folded. It has a terminal helix that has to dock here. But suppose that this terminal helix swings around and actually docks here. This is not the correct state it wants to dock, and the energy is not going to be minimal here, so it's going to be unstable. But before you can make it to the correct native state, you have to get out of this, go back to the state in which this swings around, and then dock. Okay? So this is called a kinetic trap, because a trap is something that you have to go and come back before you can move on to the final state. This is also called an off-pathway intermediate. You might say, how important this intermediate, so the information about the existence of trap is not negligible. Think about a very, very, very deep trap. Say, I have my protein. When it makes it to a native state, it becomes virtually stable. Well, of course, it can spontaneously unfold at some point, but we can think about it as a very, very stable state with, say, seconds time scale residence time. But this is not what I'm interested in studying, because I'm interested in studying the folding process. So whatever happens once I reach the folding state, I'm not interested. Okay, so let's get this out of the way. This misfolded state, let's call it this way, this trap, might have lifetimes of half a second, maybe very long-lived. So if I ask myself, what is the probability to find a particle at x conditioned to be a transition path? This might well be picked into the trap. You're still on a transition path because you went from the reactant and eventually go to the product. But the probability might simply happen to be very, very much picked here. So the problem with only dealing with m of x is that m of x may be maximum in region of configuration space that are irrelevant for productive events. They are relevant because maybe you want to build a drug that binds to one of these. So they're not irrelevant. So the information in MX, which knows about the traps, may be important. But MMX alone doesn't tell me what the really productive pathway is. Right? But now we know that a productive pathway must go in the direction of increasing committer, right? Well, it turns out that you can define a vector current, a vector field that defines the flow probability during the reaction. It's called the transition path current. And it tells you basically is the probability flow associated to making the system in the reactant and counting only the processes that go to the product and measuring where the current goes, right? I could give you a formal definition. You put an hypersurface, you count how many times at t minus t are on the left and how many times you're on the right, minus the times they fall from right, left, whatever it is. But it's clear that there is a current that tells me that the current goes this way. It doesn't go here. Why? Because anytime you go up, you have to come back, right? So the flux of the productive current of any surface that separates here and there must be zero. So there is no current in the trap. Because this is the definition of off-pathway. An off-pathway state is a state where the transition path density is finite, but the current is negligible. Okay? Well, the transition path current, J, turns out to be a constant, which I will not need to, well, the diffusion constant. Gradient of Q, but it's a constant, never mind. Gradient of Q times Boltzmann with a proper normalization. Although I didn't prove it to you, it makes sense. The current is negligible in configurations that are never visited at equilibrium, right? So if the Boltzmann weight is very low, the current is zero. In configuration, the current of probability in configurations in which I have my molecule completely unbounds all the chemical bonds and forms new one, or I have incredibly stretched chemical bonds, this is zero, there's no probability flow there. And follows the gradient of the committer. Because it tells me I'm moving from a configuration to a more likely to reach the product. So transition path theory will give me all the information about the reaction mechanism by combining these three pieces of information. Now people have reached neural network representation of Q from which they can infer M of X. I'm not aware of any neural network representation of the current because it's a high dimensional object. Think about training the 3n dimensional vector field in the neural network representation. However, it's a conceptually sound concept that you want to have in the back of your mind, that you need both the current and the transition path density to characterize, and the commuter to characterize transition processes. Okay? Okay, any questions?
I'm not sure I get why J is a 0 indeed. I get the argument about the, if this is the gradient of U and
Why is the current 0 in the kinetic trap, in the region separated? Because anytime you go to the kinetic trap, you have to come back from the same route. So the total flux of trajectory that go from the bifurcation point I to the kinetic trap, and the number of tracks that go from the kinetic trap to I is 0. I want to give you an example. What is the, say you are going from Milan to Rome by car, and pretty much in Florence you have the only gas station, okay? And let's suppose the gas station is only one road. The most gas stations in the highway have one way in and a different way out. But let's suppose you have a gas station that goes into a big square, and then from the big square you have to come back out. What is the flux of cars in the street that goes from the exit of the highway and the gas station? Is 0 because all the cars that go into the gas station eventually have to get out of the gas station to make it to the destination. So there is no current of car in the highway. We have a lot of car going up, but an equal amount of car going down. As a result, the net current is 0. And in fact, if you ask yourself, what route do people take in going to the, clearly you don't see gas stations. You only see, Google Maps will give you the destination with a productive current. Because all this information about detouring is irrelevant as long as any detour takes the same road to go and to come back. Very different situation would be one in which you have alternative pathways. So, for instance, you can do this directly. Now, this would have a finite current, because some of the particles, some of the ways the trajectory gets here, make it to the permanent state without returning to this. So, there are two alternative mechanisms for reaction. One in which you go RIP, and one in which you go RITP. And these are two alternative reaction mechanisms. The current will tell me about this by putting finite current here. So, M tells me about the static properties in the transition region, but J tells me about the reaction mechanism.
It's a long question, but it's possible to put like a continuity which
Yes, there is a continuity. So, it's not exactly, so everywhere in here, the divergence of the current is 0. It's not a continuity equation. The divergence is finite here because it emits current and is negative here. But it is immediate to show that in here, the divergence of the current is 0. And I'm going to show you, actually. So, divergent of the current is a constant, forget about a constant. Divergence of grad Q times e to the negative beta U, right? But this is equal to Laplacians of U, Q, plus grad Q, sorry, negative, grad Q, grad U beta times e to the beta U, right? This is the adjoint Fokker-Planck operation of Q. But since Q is a solution of this is 0. It's actually beautiful. There's a lot of elegance in all this. Another question is, do you remember when we defined the Fokker-Planck equation long ago? We introduced the Fokker-Planck current. Is there a relationship between the Fokker-Planck current and J? It's not straightforward, and it's only under certain kinetic condition. And let me not imagine. There, you can define kinetic regimes where the two things are identified. And typically, it's when all the population is the reactant, and you start to see flow towards the product. And in that case, you can identify the Fokker-Planck current with the transition current. Of course, when we start having back reactions from the product back, then the things start to become, okay? In the single crossing regime, two things agree. And I think, I don't know whether, yeah, I would stop here. L'ultima lezione, io farei così, I will do the following. On Thursday, I do one more lecture on maybe quick applications of machine learning, other applications of machine learning to build simulations. More like for you to be aware. Any application I'm telling you about machine learning is for cultural background, not for the exam. In the exam, I will ask you the concepts. But since the course is called machine learning, I wanted to give an insight that all the machine learning and the molecular simulations are intimately rooted at the level of statistical physics, not at the level of make prediction like before. And then in the last lecture, we're going to discuss research topics and possibly exercises you might do with your deadline for the exam and how to organize that. Okay? Very good.